final speaker during this first oral session will be Brandon Schurter from Berea College. He's been working under the guidance of Chris Fink here at Ohio Wesleyan, and he'll be discussing synchronization properties of heterogeneous neuronal networks.
All right. So, as mentioned, I'm Brandon Schurter, and I worked this summer at Ohio Wesleyan University with Dr. Fink to study neuronal networks, and in particular, their synchronization properties. So, synchrony occurs in a network when all the neurons are firing simultaneously instead of just randomly. And we are interested in this because it has been associated with a number of important brain functions, including memory formation, directed attention, and visual identification. On the flip side, it has also been associated with disorders like Parkinson's disease and epilepsy. So there are two main factors which influence synchrony in a network. The first being the dynamics of the neurons that comprise the network. Of course, there are many different kinds of neurons and many ways you can classify their dynamics. So I'll get into more detail on this later. The other factor is the structural connectivity of the network itself. As you might imagine, there's a number of ways you can connect a network of neurons. For simulating structures in the brain, there are two main models that are used, and I'll also get into more detail on these later in the presentation as well. So just to give you an overview of what we'll be talking about, first we're going to look at the details of neuronal dynamics and network connectivity and how those influence synchrony. Now, the theories we'll be looking at for these have only been developed for homogeneous networks, where all the neuron dynamics are the same. That's not really realistic when you're considering the brain. So for our research, we looked at heterogeneous networks and their synchronization properties. And from this, we might have some insight into how certain kinds of networks can be hijacked to synchrony in epilepsy. So first, how do neuronal dynamics affect synchrony? Well, as I mentioned, there's a number of ways you can characterize neuron dynamics. For our purposes, it's useful to classify them by their excitability type, which is just a way of measuring how a neuron responds to a stimulus. These PRC, or phase response curves, are a way of visualizing excitability type. I'm not going to go into all the detail of these, but what's important is that there are two main classes of excitability into which neurons fall, called type 1 and type 2. And type 1 neurons are characterized by having a positive PRC, meaning they only respond to stimuli by speeding up their firing rate, whereas type 2 neurons can either speed up or slow down their firing rate. Of course, these two neuron types have been shown to synchronize differently in networks, as can be seen from these simulation results. So this is called a raster plot, and it's just a way of visualizing network activity over time. Each neuron in the network is given an arbitrary ID, and whenever it spikes, we just put a dot. So when you see vertical lines, that means all the neurons are firing at the same time, which is synchrony. So clearly then, type 2 neurons synchronize much better than type 1s. And what's important about this is that the structural connectivity of these two networks is exactly the same in both cases. The only difference being the types of neurons in the network. So that's kind of an overview of how neuron excitability affects synchrony. What about when we get to network connectivity? Well, within the past decade, a very elegant and very general approach to this has been developed called the master stability function. To get an idea of how this approach works, take a look at this general equation describing the dynamics of a network. X is just a vector array containing the dynamic variables of the neurons. F of x is a function describing the neuron dynamics, and L is a matrix describing the network connectivity. So to give you an idea of how we construct this matrix, we have a very simple 3-neuron network and its corresponding 3x3 connectivity matrix. If we want to make a connection, say from neuron 1 to neuron 2, we simply put a 1 in the first row, second column of the matrix. To create a connection from neuron 1 to neuron 3, we put a 1 in the third row, first column of the matrix. And wherever we don't have connections, we simply put a 0. So you can kind of see how this matrix is constructed. But how does it help us determine synchrony? Well, for a homogeneous network where all the neuron dynamics are the same, it can be shown that a synchronous state exists. And this connectivity matrix helps us determine the stability of that state. So what do I mean by stability? Well, consider a marble in the bottom of a bowl. If displaced from equilibrium, it's just going to roll right back because that's a stable state. But a marble on top of a bowl, if displaced, is going to roll away and not come back because that's an unstable state. The master stability function characterizes this stability by what are called Lyapunov exponents, where a negative exponent corresponds to a stable state and a positive exponent to an unstable one. So for our network to have a stable synchronous state, the Lyapunov exponent of each neuron in the network must be negative. That is where the connectivity matrix comes in, specifically its eigenvalues, because the master stability function provides a mapping from each eigenvalue to a Lyapunov exponent. And this mapping is determined by the dynamics of the neurons. So we don't want to have to calculate Lyapunov exponents for every network we create, because that's very difficult. Instead, we pay attention to this part of the curve that's negative, because this negative curve is typical of most neuron dynamics, and any eigenvalues that fall within this region will yield the negative Lyapunov exponents we're looking for. So we want a narrow spectrum of eigenvalues. To get a measure of the spread of our spectrum of eigenvalues, we just take the ratio of the largest to the smallest, and that gives us a measure of our network's propensity for synchrony, where a smaller number means a higher propensity for synchrony. So we use this master stability function approach to characterize the synchrony of, or the propensity for synchrony of two common network models that are used in modeling brain structure, the small world model and the scale free. So the small world, you start with a regular network where each neuron is connected to its nearest neighbor. And from there, you define a rewiring probability that randomly rewires a certain number of the connections. So as you increase this randomness, you transition from a regular network to a completely random one. And the master stability function indicates that as the randomness increases, the network's propensity for synchrony also increases. Now then, for the scale-free model, it is characterized by having a few highly connected hub cells, which makes it useful for modeling parts of the brain with epilepsy, where it is thought that hub cells play a role in hijacking the network to synchrony. What's interesting about this model is that it has the same propensity for synchrony as a random network. But we know that this master stability function approach for characterizing synchrony is only valid for homogeneous networks, where all the neuron dynamics are the same. That's not very realistic when considering the brain, which we know has a wide variety of different kinds of neurons. So we wanted to see if any differences arose in the actual synchrony of these two networks when heterogeneity was introduced. So when you have a mixture of type 1 and type 2 neurons. First, before we compare the scale-free and small world, let's take a look at how the small world itself, the random small world, transitions from a type 1 network to a type 2 network. So here we have network synchrony versus the percentage of neurons that are type 2. And as we increase from a fully type 1 network, increasing the number of type 2 neurons till we have a completely type 2, you can see a steady increase in synchrony, which is what you might expect since type 2 neurons synchronize better than type 1s. Comparing that to the scale-free model, when we first noticed that in the extremes of a fully type 1 network or a fully type 2 network, both the scale-free and the random model have the same synchrony as predicted by the master stability function. However, in this scale-free model, when we position these type 2 neurons as those hubs, the most highly connected neurons, there is very different synchrony, much higher in the scale-free than in any other situation. This can also be seen when we, in the raster plots, say for 25% of the neurons being type 2. Here, where those 25% are the most highly connected, there is much greater synchrony than in any other case. So, in conclusion, different networks can synchronize differently depending on where you put the types of neurons in them, even if they have the same propensity for synchrony according to the master stability function. Furthermore, type 2 neurons can very easily hijack a scale-free type 1 network to synchrony if they are the hub cells of that network. This is particularly interesting since it is thought that in epilepsy, hub cells play a role in hijacking the networks to synchrony. So, our time's up.
Okay, thank you, Brandon. Questions?
So the type 2 neurons, when they're excited, they either speed up or slow down?
They can speed up or slow down depending on when they receive their stimulus.
Do you plot both as the same? Like if it's sped up, would you put a dot? It's slowed down, you would put a dot?
No.
Or
No. So let me get back to that plot. Okay. So this negative part is when it slows down, and this is for when it speeds up. So this phase basically tells us when, during the neuron's normal spiking, if it's not receiving any stimulus, it's normal spiking, when do we give it a stimulus? And that's just, so for the type 2s, if we give it a stimulus early, it tends to actually slow down its firing rate. And if we give it a stimulus later in its normal spiking frequency, it gives us a higher, it speeds up its firing rate.
so for your experiment, did you give the stimulus later in the phase?
So for these simulations that we ran, we just connected, so we don't actually, like here when we're running these simulations, we don't particularly say, okay, you get one stimulus, you get another stimulus. We have all the neurons connected. So when one fires, it gives a stimulus to all the neurons it's connected to. And when it receives that stimulus determines how it reacts. Type 1s just always speed up their firing rate. Type 2s can speed up or slow down.
So the PRC is something you obtain experimentally in a very controlled condition, but it gives you insight into how neurons will behave when they're hooked up in a network, because the controlled stimulus you give it is meant to mimic the signal that it will get when another neuron that's connected to it fires in an actual network. So because type 2 neurons can, in essence, both speed up and slow down, you can, in a hand-waving explanation, you can say they're more flexible, and that's what allows them to synchronize better. So there's obviously better mathematical reasons to show that.
Other questions?
Yes.
I wondered about a very simple point that you made. So when you were looking at the small world configurations, and you said that in the nearest neighbor arrangement, the very regular arrangement, that synchronicity is harder to obtain than in the random setup. Could you motivate that at all? Is there a simple way of thinking about that, why that would be true?
Yeah, it's.
Show the video.
Show the video? Okay. This is fun.
Is it in your folder?
Yeah, it's in my folder.
It's right here.
So this is this shows the behavior. This is a simulation really of a regular network. And so what sort of happens is there's no long range, the signals just propagate through as waves, and when they meet each other, they cancel each other out because of how the neurons fire and has this little lag time at the end. And so a wave just ripples through and there's no synchrony. And then we can compare that to, let's look at here, where we've got much more random connections in the network, a lot of random connections. And it just suddenly has these huge waves of synchrony throughout the whole network. So, yeah, it's very cool.
So in the first case, it's highly ordered,
Yes.
but it just passes through.
It just
and then-
passes through
and then
because
fades out,
of that order.
and then
It
it's
just
gone.
passes through. It's just like waves rippling through a lattice. So once they're gone, they're gone.
Of course, if your lattice size
in normal lattices,
Yeah.
not in these. Because when the waves meet each other, they just stop. Because of the way the neurons behave, they can't let two waves cross the waves pass through them. It's just, it's weird. But yeah, that's the way they do it.
Any other questions? Okay, let's thank Brandon again.